Hello. Welcome back, everybody. We're going to finish Markov chains today, and I'm going to then give you a conceptual introduction to maximum entropy, which will be our foundation for generalized linear models. So let's get to it. This is where we stopped on Wednesday. We were checking our chain. So we had just run a Hamiltonian simulation to remind you what this business is about. In actuality, in your computer, your model becomes a particle in n-dimensional space, and it is flung around. This is not a metaphor. This is actually what is happening inside your computer. Well, this is actually happening inside your computer. That's what it is. It's a simulation it's a physics simulation, and the position of this particle provides samples, and then those samples are strung together in what we call a Markov chain. And so when you look at these plots, they're called trace plots. You're seeing the sequential draws from the Markov chain. So each sample comes from an independent flick, simulated path of our particle. What you're looking for is largely uncorrelated sequential draws. That means it explores the target distribution efficiently. And so what that manifests as in the trace plot is what I call the hairy caterpillar that you see on the left, or white noise. And it's stationary. It finds the target distribution and it stays there, and it rapidly zigzags back and forth. That's what you want to see. What don't you want to see? Well, I'll show you examples of that on the subsequent slides. But this is what you like. You see this, and it's like, that's a healthy chain. This is what I call the ocular hairy caterpillar test. If you zoom in, of course, you see on the right here, I've taken that little section of exactly 100 iterations, 100 sequential samples, and drawn those out, and you can see how it's zigging around, right, and on the micro scale, and when you compress them all. There's other things that we're going to need to talk about here. The first half of the iterations are warm-up here. It isn't always a half. It's an adjustable amount, and I want to tell you what warm-up is. And then we're going to talk about some diagnostics, some numerical diagnostics to help you understand these chains as well. It's not enough just to check one parameter. This is a 5-dimensional posterior distribution, so you get 5 of these trace plots, and when you plot them, you'll see them all. This is only one chain. I'm going to advise you in a little bit you want to run more than one chain, and so then they get stacked, and then you want to see that they all overlap in addition. I'll show you some examples when we go. Does this make sense for now? In my experience, most people have seen Markov chains before, and no? Okay, well, welcome to the club. This is what you're looking for. This is a very healthy chain. This is what you want to see. Okay, what is warm-up? Warm-up is the period during which the NUTS algorithm, the no U-turn sampler, is adapting the step size. It is figuring out how to efficiently explore this target. It's not drawing samples from the posterior distribution yet. It's a complicated artificial intelligence that is trying out proposals and tuning the acceptance rate. So the warm-up makes the chain work well. It gives you good samples, but then it gets thrown away. It's reported to you in the trace plot so you can see how the adaptation unfolds. But it's diagnostic. It's not something that's used for inference. So every time you do some inferential step, like get summaries of the parameter distributions, the warm-up is not included. But it'll be shown on the trace plots. Those of you who've run other kinds of Markov chain algorithms, like Metropolis Hastings or Gibbs sampling as a special case of Metropolis Hastings, you may be tempted to think of the warm-up phase as burn-in, but they're fundamentally different. So we're not going to do Gibbs sampling in here, so we're not going to talk about burn-in, but I just want to say that it's burn-in samples are from the target. They are. They're perfectly good samples. That's not true of the adaptation samples, and that's why they're thrown away. So you just want to think about them as fundamentally different things. Okay. Convergence diagnostics. The two that are reported in the Précis output are the two most common, and ones you want to check. These are not fail-safe devices, but they give you good warning information about when things are wrong and the quality of the Markov chain. Let me explain them, and you'll fully understand these through worked examples, and I'll show you what happens when the chain is bad to these criteria. The first is N_F. This is the number of effective samples. There's a formula for this, so you can look it up, but the intuitive understanding of this is there's the total number of samples you took from the chain. Say it's 1,000, like in this example. Your effective number of samples is always going to be less than that, nearly always. Sometimes the chain is so awesome that it will be the same. That happens occasionally with really simple models. But usually it'll be less. And that's okay. That arises from the fact that the samples are correlated with one another sequentially. And so there's still, Hamiltonian Monte Carlo is good, it's better than other things, but there's still some correlation, right? The paths aren't completely independent of one another because there's an origin and there's a destination, right? And if the target distribution is really vast and highly dimensional, you don't get infinitely far from where you started on each path. So there's some autocorrelation. That autocorrelation means that there's some redundant information in the sequential samples. And so NF is calculated by looking at the correlation between subsequent samples and then doing a statistical adjustment to say, effectively, statistically speaking, if we had a chain that was where subsequent samples were perfectly uncorrelated with one another, how long would that chain be before it gave you the same information as this one? Should I say that again? It's good. This is where English needs grammar, right? I need some cases to mark what's modifying what there. But so I'll try to say that again without so many embedded phrases. So you imagine a chain where each subsequent sample is perfectly uncorrelated with the previous sample, right? Perfectly. So you'll never get this chain, but you can get close to it and stand, but you never get it exactly. Now, say you run that chain 200 time steps. Okay, when you see NF of 200 on a real stand chain, that means that that's how long the analogous uncorrelated chain would need to have been run. Now you ran this one for 1,000, so it's like you lost 800 samples, right, compared to the perfect chain that you'll never realize. Does this make some sense? It's giving you an idea of the inefficiency of the chain in terms of information. It doesn't mean there's anything wrong. It's still valid samples. It's still telling you about the target distribution, right? It's a feature of Markov chains is that they have serial autocorrelation. That's okay. It's just giving you an idea about how much autocorrelation there is in this chain, how inefficiently it's running. If a number is very low, the chain may be totally broken. And I'll show you an example of this. So how low is totally low? Well, it's a continuous range of alarm. But a good heuristic, I would say, is if your number of effective samples is 10% of your total samples, you should be very, very alarmed. And I'll show you an example of that in just a couple minutes. Okay? Typically, it's high, and then you might say, well, how many effective samples do you need to make inference? Well, the central limit theorem saves our bacon again. How many samples do you need before you know the mean of a distribution? Right? And the answer is like 20. Right? So if you have 200 effective samples, you know a lot about a parameter. You don't need 10,000 samples. That said, if your scientific question depends upon knowing the 99th percentile, the shape of the tails of this target distribution, you're going to have to sample the hell out of this thing, like really slam it, like 100,000 samples. That's really hard to do, to sample tails, and that's true of any sampler. It's just a problem. But if you're interested in the mean and 80% interval, 200 is a lot. That's a lot. That'll do you. Okay. R hat. This is the hat, by the way, means a circumflex on top of the R. But I like to write it like it said. It's always said R hat. So this is the Gelman-Rubin diagnostic. It's an F statistic. Those of you who love F statistics, have had a course in F statistics before. If you haven't, that's okay. I'll explain what that means. It's a ratio of variances. So you can think about, we're going to run multiple chains, independent Hamiltonian Monte Carlo simulations on the same data and model, drawing samples from them. And then we look at those chains side by side. The first thing we want to see from the, what I call the ocular hairy caterpillar test is that they converge to the same central values, You can just do that by seeing if they overlap. But they're still going to be different. Some of them will go up while others go down, and then the question is, are they really sampling from the same target? That's what you want to make sure. And so what you could ask is, okay, each chain has a certain amount of variation within the chain through time. There's variance within each chain in the parameter values that are drawn. And that's the variance of the target, right? So there's a Gaussian distribution, say, and it's got some variance, some width. And that's the variance within each chain should converge to that. And then there's variance between chains. And as the chains run long, you want the variance between chains to be the same as the variance within chains. Why? Because they're drawn from the same distribution. That should be the case. So the ratio of the variance between chains to the variance within chains should converge to 1. That's what you want it to do. I'll say that again. The ratio of the variance between chains to the variance within chains should converge to 1. And this is the Gelman-Rubin diagnostic. Now the actual calculation is more complicated than the way I just verbally explained it, because you have to do these adjustments for sample size and other fun things. That's cool. Stan does that for you, and then it prints it out in this table. This R-hat is actually sophisticated because it's using time variance and other things to be super alarmist about things that might go wrong. So one of the things I like about Stan is that the coders are super alarmist. This is what you want in your software, is for it to be paranoid. Right? It's this smoke alarm principle. Yes, you were just cooking a cake, but the smoke alarm thinks there's a fire. That's what you want your software to be like. Yeah, and so that's the way Stan is built. It will be fire alarms going off all over the place, and that's good. Sometimes it'll be like, no, it's a cake, and you figure that out. There's not actually a fire here, but you want your fire alarm to wake you up. You don't want to die in your sleep, right? That's how it goes. And that's the way it is with your Markov chains. It's a bit of a macabre metaphor, but you're welcome. We look at R-hat here. They're all 1. That's what you want to see. If they're a little bit above 1, that's probably okay too. You might just try running the chain longer and get them to converge to 1. Sometimes they'll be really, really big. I'll show you an example of that in a moment. Okay, are you guys with me? The interesting thing, of course, is that both of these diagnostics can look fine and your chain can still be awful. So you need to check it different ways and use your judgment. There's just no way to fully automate these things. Okay, so let me show you some examples before we stop looking at Markov chains of chains gone wrong. So here's a toy example that illustrates a general problem in running Markov chains. A problem of having too diffuse of a distribution to sample from, and you can fix it by adding, well, some priors, some weakly informative priors. These priors will have no effect on your inference, but they will allow you to get an inference. This is a very common problem in Markov chains. So the teaching example here, we have 2 observations, and they are of value -1 and 1. And we want to estimate the mean, the standard distribution of the process that generated these. So the mean should be 0, right? And you probably have an educated guess about the standard distribution you might estimate. So we make a model here. What I want you to notice about the model on the screen is that it has no priors. So what does that mean? If you don't program priors into the formula list, they're flat by implication, because that's the way it works if you leave them out. Because a flat prior just multiplies the posterior by a constant at all parameter values. And so you might as well just drop it, because constants can be dropped from these calculations. Yeah. This is why you need priors, lesson number 200, right? And then I start the chain. There's a start list. We don't often use this. I started at a mean of 0 and a standard deviation of 1, which are very excellent guesses. This is just to demonstrate that the pathology does not arise from starting in a terrible place. And then we run the chain, and you see the Précis output on the bottom. Something's wrong, yeah? You probably don't need NF and R-hat here. You just look at the parameter estimates themselves. Something is wrong, yeah? Don't publish this estimate, yeah? So, but look at NF, 7, 72, and R-hat 1.36. Look, R-hat 1.02 for sigma, that doesn't mean it's okay, right? Although 1.02 is not a terrible R-hat, but that doesn't mean it's okay. What are these? The trace plot is usually the best diagnostic. You want to always look at trace plots. And these trace plots are bad. This is a bad trace plot. Yeah, there's 2 chains here, 2 independent chains. One's One's in black and one's in blue. Apologies, those aren't the most fantastic colors, but they work well in print. And you'll see that they don't look anything alike. The blue one is just flying all over the place, out to really high values. That's why you get these strange parameter estimates. It's going up to 2.5 times 10 to the 8th. It's a big number. It's pretty far from 0. Yeah. And the black one is just stuck. It's not moving at all. And then for sigma, the blue one again is just leaping all over the place as it tries to cope with the wild slings of alpha up there. The chain is having fun, but it's not getting a good inference. So what's gone wrong here? Come on, computer. The problem is that the priors are flat. And flat means flat forever, out to infinity. And the great thing about Hamiltonian Monte Carlo is, remember, it's a physics simulation. And there's this big frictionless bowl. And if your bowl goes out to infinity, then the particle will seek infinity. So it's just doing what you asked. So there's this hockey rink with very gentle curvature going out really, really far. And Hamiltonian Monte Carlo sees the gradient, right? There's a little puck that's rolling along. And so it's doing what you asked. It's like, okay, I need to take occasional samples from infinity. Let me try that. And so there are these wild simulations that go flinging way out there and take samples. But obviously, your a priori knowledge is that infinity is not a legitimate estimate. So you might want to put a prior on there that rules out infinity. It's a good idea. And so that's what we do, and that's one of the reasons to use these weakly informative priors. They contain very little information, but they rule out infinity, and they allow you to get stable estimates. These problems arise in other kinds of samplers as well, like Metropolis-Hastings samplers, but Metropolis-Hastings samplers don't send off alarms like this. When they're unhealthy, they look like the same as when they're healthy. And so one of the major advantages, in addition to the efficiency gains of Hamiltonian Monte Carlo, is when it breaks, you can tell. It looks really, really different when it breaks. Metropolis-Hastings looks like a random walk even when it's working. So it'll randomly walk here, and it doesn't see the curvature. So it doesn't take these wild samples, but that doesn't mean you're getting the right inferences. Yeah, so this is a big benefit, the fact that it overreacts like this. So how do we fix it? Let's just add some weakly informative priors. I'll put a normal 1, 10. I put the prior at 1 here to show you that it's not going to matter. It'll still find the right mean. And a half Cauchy 0, 1. Very diffuse priors. Here's the code, of course. You know how to do this. You're good at adding priors. And now it's sensible. Alpha is indistinguishable from 0 there. The NFs and R hats are great. Perfect. Yeah? You also notice you should run these at home. The code's in the chapter. You should run this example yourself. One of the things you'll notice is the bad chain also goes real slow. So you'll start to develop intuitions with your own personal machine, because you know how fast it is and how capable your little robot is, that when your chain is broken, it's gonna warm up real slow. That might make you start to worry. And then the good chain goes fast, because it doesn't have to struggle. It's not taking these really crazy paths out. There's this thing called the expression tree that you can read about in the Stan manual that help you understand that. Okay, so here's the good chains against the bad chains. You see the good chains again, hairy caterpillars, right? I guess for a scale parameter like sigma, it's not really, but now it's the side view of the hairy caterpillar, right? It's only looking at the hairs go up, and it's lying, it's resting on the bottom. Yeah, the metaphor doesn't really work in all contexts. Okay, another example. Oh no, this is the same example, sorry, just to show you where the priors are. The priors that I put in this example are the dashed lines. There's your half Cauchy, and the posteriors that are inferred. So these are very weak priors. They have no effect on inference except to make it possible that you get an inference that's trustworthy. Now, this is what these weakly informative priors do for you. In high dimensional models, this gets even more important, is to do some regularization of this kind. Okay. That's also a reason, by the way, that maximum likelihood inference is bad news, right? Because they have flat priors. Okay, so one more example, and then we'll move on to maximum entropy. Here's a case that happens because We're not omniscient when we design models, and sometimes we code redundancies of parameters into them. This can happen by accident. It can also happen because the model forces it. We won't have examples like that in this course, but it'll come up in your life. And so here's a case where I'm going to force it, and it'll be obvious to you that this is a mistake. But there will be other cases in your life where it will arise by innocence, and then you want to recognize that this happens and know how to fix it. This is like the left leg, right leg thing, but in the purest form. So we have a model. I draw 100 samples from a normal distribution, and then we're just going to estimate the mean and standard deviation of this normal distribution. But in the model specification, I'm going to have a redundant intercept. I'm just going to have two parameters for the intercept and add them together. There's alpha 1 and alpha 2. Now, there's an infinite number of ways to add two numbers together to get the same sum. It's a fun thing about arithmetic, right? And so that means that the specific values of alpha 1 and alpha 2 are unidentified. You can't say what they are. You can identify the sum of these two numbers, but you can't identify the components. But Bayesian inference is capable here, and it will do what you ask. It will give you all the pairs of values that make the sum that is identified by the data. And it'll have fun doing that. Notice again, I don't have any priors on alpha 1 and alpha 2 is what makes this degenerate. We're going to fix it by putting some priors on it. So Tracy at the bottom, I hope you recognize that that's bad news. You should notice that the sign of alpha 1 and alpha 2 is perfectly inverted, right? Because they sum to 0. Yeah. They're also highly correlated one. Look at those confidence intervals. I like that standard deviation. That's a good one. And then R hat, NF is 1, right? That's like your bottom case. It's hard to do worse than 1. Okay, let's look at these chains. So this is a very high-res slide, and my computer is struggling to show it. There it goes. All right, so those are the chains for alpha 1 and alpha 2. I ran 2 chains in this model. You can see so there's a black chain and a blue chain. You can see that they're exploring completely different parts of the space, but you'll notice that A1 and A2 are reflections of one another in any particular chain. Can you see that? It's a consequence of the sum being identified, but the independent values not being identified. Sigma's doing a little better, but that's not a great chain either. NF is 17, right? So let's fix it. We put some weakly regularizing priors on A1 and A2, and this works. This is great. Yeah, you still just want to take the redundancy out of your model, but like I said, there are model types where you can't totally take these redundancies out, and you use priors to identify one of the components, and then you get stable inferences. So looking at the slide again, the left is the old bad chains. On the right now with very weak priors, which have no effect on inference, except that, of course, they let you get an inference. Hairy caterpillars, as far as the eye can see. This is what you want to get. Yeah? So in my experience, when students and colleagues are having trouble with their chains, it's because they forgot to put a prior on a parameter. It can happen. You start adding a bunch of parameters to your model because it's fun, and then you forget to put a prior in for one. Yeah, it happens. And then Stan does what you told it to do. It tries to sample infinity. And that doesn't work out so well for you. So you got to just check. And so lots of people send me their code. This chain's not mixing, Richard, help. This is like part of every Monday morning for me. And the first thing I do is, okay, how many parameters do they have? Is there a prior for each? Nope, that one's not. It doesn't have a prior. Put it in, run it, works. That's the number one thing that happens. It's a perfectly innocent mistake. There's no shame in making that mistake. I do it myself, right? And then I notice it and I fix it. That's just how it goes. Okay, your homework to practice this. You really got to get in there, install Stan, and run these examples and start to get some sense of it. And so I suggest the first 3 hard homework problems, which build on these broken chain examples. And help you understand how these things work. There are, as always, additional hard problems after these 3, and if you're feeling excited, you should do them. And if you have questions, of course, I wrote the problems so I can help you. And I'll give you the solutions too to these things after you turn in your answers. Next week, we're going to work on generalized linear models. This is chapters 9, 10, and 11. And then next week, we're going to start holiday break. Okay, it's Christmas season. and people will be fleeing. And then we'll resume in the new year and we'll finish the book. Okay? So in the remaining time today, I want to start chapter 9. And this will be conceptual work. The point of the material I'm going to launch into now isn't that it establishes particular algorithms you're going to run, but rather it's the philosophical justification for a set of common choices. And it's one of many ways to justify the choices that we're going to make for generalized linear models. But it appeals to me, and I want to try to make it appealing to you because it's conservative. It entails very few assumptions that make it seem reasonable, and it doesn't aspire to say that it makes up happy answers for us. It basically accepts that the universe is hostile to human life, and inference is hard, and it goes from there. So with that note, stop thinking about stats for a minute and think about pebbles and buckets. So imagine you have 5 buckets. You line them up. Say I line them up on the wall over there on the other side of the room, and I've got a stack of 100 pebbles. On each pebble, one of my graduate students has painted a number. Numbers from 1 to 100. All right, had my minions paint numbers on rocks, and now I'm going to throw each pebble one at a time in such a way that it is totally unpredictable which bucket it lands in. There's an equal probability it lands in any of the 5 buckets. So if I'm far enough and a bad enough throw in exactly the right way, you can imagine this works, right? So we throw the 100 pebbles into the buckets, and as you can imagine this experiment, right? So what are all the possible counts of pebbles? How many pebbles end up in each bucket? Now, this is something we want to think about before we've done the experiment, or you could just do the experiment a bunch of times, right? Imagine we employ, the whole country of Poland in throwing pebbles, right? So every Polish citizen, I don't know why I picked on Poland, but I'm not picking on Poland. It's what I thought of. We give every Polish citizen 100 pebbles, and they have to throw them in the buckets, and they report, right? So then we'd have a big data set of the distributions that arose, and we could think about that distribution of distributions. I'll say that again. There's a distribution of distributions now because every Polish citizen has contributed a distribution of pebbles. Now we've got this collection of the arrangements of pebbles in the buckets, and we want to say things about that, about the frequency with which different kinds of distributions arise. So the first thing would be to say, well, what kind of distribution is most plausible to you a priori? And I bet you have good intuitions about this, but I want to help you justify that intuition in a way that is maybe a little bit strange to you. So first, let's imagine a really weird distribution. Say all 100 pebbles land in the first bucket. It'll happen if we get all of Poland to go along with this experiment. There will be some lucky farm boy who will, in the south of Poland, who will be able to do this. It's a beautiful place, by the way, southern Poland, and I recommend visiting. And he will be lucky enough to do this, even blindfolded, right? And he will do it, and then a religion will start or something around this person. But this will not happen very often, right? There are a bunch of distributions of this kind where all the pebbles end up in one bucket. And the names of the buckets don't matter here. So all these distributions are in a sense of the same type, right? Where all 100 pebbles end up in one bucket and all the other buckets are empty. Yeah, you follow? And those are highly implausible. We're going to justify that intuition in a moment, or what that means. But I think you agree. You find that implausible. It won't happen very often. There are lots of other distributions, really high number of different arrangements of pebbles in buckets, which are going to look more even, right, but are still uneven to some extent. And in fact, most distributions are uneven. The even distribution is one special kind of case, right, where all the pebbles are exactly equally balanced in all of them. So we can do some statistics on these things and then think about, well, what is, in this universe of distributions that we've got, the distribution of distributions, what is the thing that will happen most often? Or what are the numbers of ways you can get different arrangements? And this will help you justify the intuition about why having them all in one bucket is highly implausible. So let's think about the numbers of pebbles in each bucket. Let's just assign symbols to them. N sub 1 is the number of pebbles that end up in bucket 1, N sub 2 in bucket 2, and so on. with me? And then you learned in secondary school and have probably forgotten if you're a healthy human that you can calculate the number of possible ways to arrange pebbles in these buckets. And this is a thing called a multiplicity, and you learned this in combinatorics. And then, like I said, if you're a healthy human being, you moved on to more important things in your life, and you have since forgotten this, right? That's a perfectly healthy response. But now we'll be back. And so this thing is called the multiplicity, often written capital W. I don't know why, but it's often written capital W. And it's in factorial over the products of the factorials of each of the counts. And this is all the different ways to arrange, given that there's N1, N2, N3, there are individual pebbles. This is what we're dealing with, right? So it doesn't matter if pebble number 1, right? Remember, Natalia dutifully painted numbers on each of my pebbles, and right, it's a condition for your PhD. And it doesn't matter if pebble number 1 is in bucket 1 or if pebble number 2 is in bucket 1. It's just a number of pebbles. The identities of the pebbles don't matter to us. It's just, so how many anonymous rearrangements of individual pebbles will give us the same distribution of these counts in 1, in 2, in 3, and 4. Yeah? And this expression gives you that count, and this is called the multiplicity. It's the number of unique arrangements of the pebbles that gives you the same distribution. I'll say that again. It's the number of unique arrangements of the pebbles that gives you the same distribution. There's all the pebbles are these little microstates, and we're not counting the particular identities. We're interested in the shape of how they've ended up, right? We don't care if it was your first throw that went in bucket 1 or your 10th throw. It's just how many throws landed in bucket 1. You with me? And this multiplicity turns out to be super important for understanding why some distributions are more plausible than others. And the reason is because there are vastly, vastly, vastly many more arrangements of the pebbles that will produce them. And here's the intuition. There's a slide that's going to build this up, but I want to get the verbal statement out first. Every distribution is unique of individual pebbles, right? And it's random. So every unique arrangement of the pebbles is equally likely. So having all 100 pebbles in bucket 1 is just as likely as having all 100 pebbles in bucket 5, which is just as likely as having pebbles, how many pebbles are there? 100? So if they're even, how many pebbles are there in each bucket? 20, right? So pebbles 1 to 20, thank you. Pebbles 1 to 20 in bucket 1, 21 to 40 in bucket 2, and so on. That's just as likely as having all 100 in bucket 1. Yeah, because it's random. But the number of rearrangements of the individual pebbles, which will give you an even distribution, is vastly, vastly big. And there's only one way to get them all in bucket 1. Okay? So let's draw this up, and so I'll give you an idea about when I keep saying vastly, vastly, what do I mean? Well, let's count it. We've got the expression W on the previous slide. That's what we need. We can just calculate this. Your computer will do it for you. So let's do an example. Now instead of 100 pebbles, let's just say 10. I need to do this for the sake of the example because the number's going to get big really fast. And if you do it with 100, you get overflow errors. So you have to start doing things on log space. So this will serve. This is an even better thing. Only 10 pebbles now. We throw them into buckets, 5 buckets. How many ways can you get all 10 pebbles in bucket 3? And the answer is 1. Is that intuitive? I'm sure it is, but you can also plug it into that expression on the previous slide. And you'll get, this is the answer it gives you. Yeah? What about how many ways are there to get 8 pebbles in bucket 3, and 1 in bucket 2, and 1 in bucket 4? How many unique arrangements of pebbles? Remember, these are, Natalia painted all these pebbles. And so we're going to take, like, just swap, right? You can swap pebbles out of the center column into the other and move them around. How many arrangements do you think? Any guesses?
90.
Yeah, the answer is 90, exactly. You can plug it into the multiplicity. So plug it in. It's 90. It's a lot bigger than 1. Yeah, and all we've done is take 2 pebbles out of the center column and put them on the adjacent ones. Now we're at 90 already. This is going to go up real fast. And this is why combinatorics is so maddening, and this is why encryption works. Right? It's the same principle. How many arrangements of symbols are there in a password? So now consider we're going to put 6 in the center column and 2 in buckets 2 and 4. 2 pebbles now. Now how many unique arrangements? I won't continue the game. This would be the worst pub game ever, right? Teams compete to do rapid combinatorics while drunk. But The answer is 1,260 ways to get this distribution. A little bit more even yet, we take 2 more pebbles out of the center bucket and put them on the ends. So now you have 4 pebbles in bucket 3, 2 in buckets 2 and 4, and 1 in buckets 1 and 5. How many ways? And the answer is 37,800 ways. This is combinatorics. It's really incredible how fast it goes up. So the flatter distributions, of course there are more ways to realize them, but it's not just that. There are vastly, vastly more ways. They dwarf it. So if you plot it out in stacks, the numbers of ways to get different shaped distributions, if you zoom out, you can't even see the uneven distributions because there will be this giant stack of ways to get the even ones. So we haven't even gotten to even yet, so let me show you that. The perfectly even distribution where there's 2 in each bucket, there are 113,400 ways to do it. And this is only with 10 pebbles. This phenomenon goes up really fast if you add more pebbles. So that's why I didn't do it with 100 pebbles, because the numbers are really huge. Like, they filled the whole slide. Huge. So you're talking about lots of little particles now. It gets even bigger. Does this make some sense? Why are we doing this? Well, this is to help you school your intuitions and have a mathematical justification for the intuitions about why, if there's a random process, which means that each little particle of plausibility, a pebble, is equally likely to end up in any bucket, then why is flat a safe bet? Why is that conservative? Why does that seem more plausible than uneven? Because each unique arrangement of the little particles of plausibility, the pebbles, is equally likely. And the answer is because there are vastly, vastly more ways to get even distributions. So whatever happens, it's likely to have that shape, because it's very, very hard for it to take any other shape. And this is exactly what happens, why the soccer players ended up in a Gaussian distribution on the soccer field earlier in the course. I'm going to come back to that example just before you guys go today. Okay, so here's the trick now. For large n, you don't want to calculate W. It gets big. The factorials, if you've worked with factorials ever in your life, but even if this isn't recent, you may recall that they get big super fast, right? So for big factorials, we need approximations. And there's this famous one called Stirling's approximation, which is actually one of the best approximations ever in applied math. It's super accurate. In the number of particles, the number of pebbles, doesn't have to get very big at all before the Stirling's approximation is almost perfectly exact. It's a really good approximation. So it's spelled Stirling, like the English city, the Scottish city, Stirling. For large n, we're going to calculate now. We're going to do it on the log scale. You'll see why in a second, but it's convenient to do things, big numbers on the log scale. 1 over n times the log of w. Why divide by n? Well, we don't care about actually the total number of particles. We want some measure of normalized measure of the relative number of ways to get the different distributions. And that's what dividing by n will do for us. Right? It just normalizes. Because the number of pebbles isn't much relevant to us. Right? It's the relative numbers of ways to get the different distributions. And then we work on the log scale because it keeps us sane. Yeah? And so it turns out, using Stirling's approximation, there's a box in the chapter where I show this if you're interested, that it's approximately, and approximately here is it's super accurate. By the time you have 100 pebbles, it's really good. Minus the sum over all the buckets, n sub I over n times the log of n sub I over n. Now, there's no punchline here yet. That comes on the next slide. Bear with me. What are we doing here? This is something you've seen before in the course. This is information entropy. This is all that weird stuff that I did with you last week, right? Wasn't it last week? With information criteria. And remember, the target in information criteria, what we're trying to minimize is the information divergence between the model we're using to approximate the true model and that model. This is what information, the Kullback-Leibler divergence is for. That the information entropy gives us the right scale to say when two distributions are different from one another. It emerges here spontaneously. It's the information entropy is the number of unique arrangements that will give you that distribution. That's what it is. There's nothing in this argument that I've just given you that has anything about information. Claude Shannon didn't appear looking macabre on the side of the slide or any of that stuff. It just arises as a consequence of saying, let's count up all the unique arrangements of pebbles that would give us a distribution of this shape. And it turns out that is information entropy. It's the normalized count of the number of unique arrangements that give you that distribution. That's exactly what it is. I think this is cool. Super cool. It's also demystifying in the sense that there's nothing about entropy that tells you how the world actually exists. It depends entirely on your assumptions. You made assumptions about how pebbles get into buckets and all that, and then you can do the combinatorics of counting it up. And information entropy is the way to compare the relative plausibilities of the different distributions, the number of unique arrangements that give them to you. This perspective on information theory, and it's actually a full perspective on statistical inference, is owes to a lot of people, including, of course, Claude Shannon. But it was the person who developed it the most is pictured here is Edwin Janes. He was an American physicist who passed away only in 1998, and he called this the maximum entropy principle, which is a conservative principle for statistical inference. And it goes something like this. The distribution with the largest entropy is the distribution that's most consistent with our stated assumptions. And that the reason is because it can happen the largest number of ways. So in the context of the pebble throwing, what does this mean? What are our stated assumptions? Stated assumptions were that each pebble has an equal chance of landing in any bucket. So now if you were going to bet, right, so we employ the whole country of Poland again to throw pebbles into buckets, and each of you now needs to place a bet on a distribution. What is a distribution that's going to happen? And the closer your bet is to each bucket, each arrangement of bucket that is actually realized, you get a euro, right? We do some scaling arrangement. So you want to find the center of gravity, right? What is the distribution that will be most like most of the distributions that arise? You should bet on flat. You should bet on an equal number of pebbles in each bucket. Not because most of them will be that, but because that will minimize your information divergence. And the reason is because there are vastly, vastly more ways to get a distribution of that type. And then the distributions just neighboring it that are slightly uneven, there are vastly, vastly more ways to get those than the distributions just neighboring them. And by vastly, vastly more, it's like a very steep Swiss mountain. It falls off so fast that if you bet on the central distribution, your error is really minimized. It's an incredible phenomenon. Janes called it the entropy concentration theorem. And it happens really rapidly in these systems. And it's also why normal distributions appear everywhere. It's the same phenomenon, but we're going to get to that. We didn't get a normal distribution here. You might be saying, why? It's because there are constraints in those systems, right? There's not a constraint here. Okay, so for parameters, this is a way you construct priors. If you have information about a parameter that provides constraints, you can then choose a prior distribution which is the most conservative but still obeys those constraints. We're not going to do that in this course, but you may see it from time to time. You want to interpret it as a conservative way to construct priors. It would be the prior that contains no other information and is minimizing its distance to the target. We're going to use it to construct likelihoods, that is data models, because the outcome variables have constraints that we know before we've seen the values of them. It comes from the experimental design or the measurement model. And then we can choose the maximum entropy distribution that contains only that information, and it's the flattest distribution possible, and so the most conservative for prediction. And that's the goal. And again, why do you want to do that? Because you want the flattest distribution, because then it will be closest to all the true things. Right? It's this thing about information divergence. Remember going Earth to Mars, Mars to Earth? If you start out with a vague prior, you're closer to the target. And that's what maximum entropy is doing. It's helping you find the vague thing that is nevertheless most consistent with all the information you think you have. That's what it has. At the bottom of this, something that is cool about it, it turns out that Bayesian updating is a special case of this procedure. The posterior distribution is the distribution that is flattest, but is still consistent with the prior and the data. There is no other distribution that is consistent with those facts. That is the information you put in. You started with the prior state. There's a prior distribution, and then there's the data you put in. That's information. The posterior distribution is the unique distribution, which is flattest and still consistent with all that information. Right? It's the most conservative answer the golem could give you, given the information you forced it to use to make an inference. And so it's the posterior distribution is a maximum entropy distribution. I think this is, again, a really cool fact about how this stuff works. Okay. We're doing good time. This is great. Okay. You remember information entropy, of course. All of you have back tattoos of this by now, right? I'm sure. No, don't do that. This would be the worst tattoo idea ever, right? I'm sure it exists on the internet now. Someone's going to send me email. What kind of distribution, the basic principle of maximum entropy we're asking, we're going to ask what kind of distribution maximizes information entropy. And we want to seek distributions like that because that gets us closer to whatever the true distribution is that would be an answer to our problem. Right? It's a conserved way of seeking conservative representations of information that embodies only the constraints we put in. So if there are no constraints, flat is the answer. It's a fact about information entropy that if all the p's are equal, then this quantity is maximized. It's a fact about it. All right, and you should do some examples maybe on paper to prove this to yourself and play around with it. And in chapter 9, I give you some graphs of this. But what about when there are constraints? Well, let's build up to that. In the case of a uniform, the constraints are just between A and B, and then entropy will be maximized when it's flat. So I give you 3 examples here. Uniform distribution in the middle, the entropy is 0. So think about the scaling, entropies can be negative. It's okay. And you still want to maximize it. On the left, we have the diagonal up, that has lower entropy. And on the right, we have this humped, and that also has lower. So there's more information in the distributions on the left and right. They're less uncertain. Yeah? So the maximum entropy distribution is the flat. And that fits your intuitions about flatness. And how do you want to think about this? Well, there are many, many more rearrangements of the little particles of plausibility of each parameter value that will give you flat. And that's why it represents a central representation of uncertainty. What about something else? Let's go back to our buckets. And now we're going to put the buckets down. What we want to impose on these buckets now is some set of constraints for them. So to visualize this well, we're going to need more buckets. So is that okay? Can we have more buckets? Okay. And I'm going to number these buckets like they were parameter values to help you understand what's going on, because that's what they are. They're parameter values. So let's put down a bunch of buckets, and I'm going to number them from -8 to 8. Yeah? And then we're going to do our pebble tossing thing again. But now there's going to be this constraint that whatever arrangement the pebbles end up in, we're going to go and we're going to census the buckets, and then we're going to calculate the variance of the numbers of pebbles across buckets, the variance of the distribution, and that variance must equal 1. That's the constraint we're going to impose. So what does that mean? Well, we're going to do a bunch of experiments, and we're going to end up rejecting a bunch of pebble toss collections, because we'll count them up and go, oh, no, the variance isn't 1. Start over, empty the buckets. Sorry, Poland, we've got to do it again, right? This is why you want your computer to do this. But if you do that process of acceptance rejection, you end up with a collection of distributions, arrangements of pebbles. They all share a common constraint. Their variance is equal to 1. But the exact identities of the pebbles are shuffled around. There are lots of distributions that will have the same variance. Yeah? You can imagine rearranging lots of things. So huge numbers of distributions over this many buckets that will have equal variance. And you can calculate these in the computer. But it turns out that the shape that is vastly, vastly more likely than any other is the Gaussian. If the only constraint you impose is that the variance, in fact, the variance be finite, but here we fix it to an exact number, of all the distributions with the same variance, the Gaussian is the flattest distribution possible that still has that variance. There is no, if you change its shape in any way, there are fewer ways to realize it. And how fewer? Vastly fewer, because of the way entropy aggregation works. So, again, there's a box in chapter 9 where I have a proof of this, if you're interested. Proofs are good for you, yeah? That's why we like math. You can actually prove things. It's not like science. right? If nothing can be proved. Sorry, it's too early in the morning for that kind of statement. I apologize. I withdraw the comment. And ask me again in the afternoon, I'll re-endorse it. But and then why? There are vastly, vastly more ways to realize the Gaussian shape. This is exactly what happened with our football players on the football pitch back in chapter 4. Whatever pattern of sequence of coin flips they got that made them take left and right turns, their distribution of positions ended up Gaussian because there's almost no way it could do anything else. Because there are vastly, vastly more ways to get a bell curve, or something imperceptibly close to a bell curve, than any other distribution. So of course that every sequence of coin flips is a unique snowflake, but it doesn't matter because those unique snowflakes aggregate to a Gaussian distribution. Yeah? This is super cool. So nature is full of bell curves because there are vastly, vastly more ways to get bell curves. Because of all the distributions that have a same variance, it's got to be a bell curve. It's just really hard to get anything else once you've got a good number of pebbles, right? So I'm mixing a lot of metaphors here, but I think you're seeing where I'm going. So the Gaussian distribution is the most conservative distribution you can use when all you're talking about is the mean and variance of a set of measurements. There is no other distribution which will spread probability more evenly across the possibilities. It seems weird, right? Because you think, but it looks like a bell. Bells aren't flat, but it's got a constrained variance. And so you can't make it flatter and have it be, well, flatter, right? And so there's a section in the book where I show you generalized Gaussians, and we can plot. So there is something called the generalized Gaussian distribution. In fact, there's more than one, but here's just for one type of that. And I'm showing you that in the generalized Gaussian, the entropy is maximized exactly where the shape parameter is 2, and that's where it's actually the Gaussian distribution, the bell curve, where it's quadratic. That's what the 2 means. It's a quadratic exponent. And it's exactly Gaussian. And that's why nature is full of bell curves. You're welcome. All right. That was really cool. I think it's cool. So, the binomial, another example. Binomial distribution, this was our globe tossing at the very beginning of the course. Remember, we tossed the inflatable globe? And we didn't actually, I just held it up as a prop. But and we sample data from it. This is the coin flipping distribution, the binomial distribution. Next week we're going to use it to do statistics again in the context of full Bayesian inference. Why the binomial distribution for counts? Right? Probably it's been taught to you the way I did it at the beginning of this course. It's just asserted. It's like angels descend. Oh, they give you a formula. This gives you the distribution if there are coin flips. This is what you use, right? It's like, okay, right? I'm mortal. Who am I to argue with the angels of math? And there's a better justification for this. The binomial distribution is the maximum entropy distribution for discrete outcomes with a constant expected value. There is no other distribution that will spread probability as evenly as the binomial. Again, it's really epistemological. Nature, it could be something else, but if you don't have any other information than discrete possibilities and a constant expected value, your safest assumption, in the sense that it is maximum entropy, there are vastly, vastly more ways to get this shape than any other, is the binomial. Cool, yeah? And there's a proof of this in the chapter. Here's the visual intuition perhaps behind it. What you have to realize now, let's think back to the Garden of Forking Data, and we're drawing marbles from the bag again. There are white marbles and blue marbles. The marbles have unique identities, again, right? Natalia has painted them. And they have ID numbers on them again. So you have to think about the different arrangements. And so if we draw just 2 marbles from the bag, there are 4 different possibilities. You can get white-white, you can get blue-white, you can get white-blue, and you can get blue-blue. Yeah? Those are 4 different things. And you've been trained in the binomial to treat BW and WB as the same outcome, but they're not. They're different things. So why should we treat them the same? And the answer is because that's maximum entropy. It's the number of arrangements to get these things. It ends up, you want to put the same probability mass on those, because that's the way, the largest number of ways things can happen. So, show you the shapes on the right. Accelerate this a bit. You should read this section. You think about a distribution like A, where it's perfectly flat here. The expected value here is a half. In this example, we have an equal chance of drawing a white or a blue. And the entropy is 1.39 for the perfectly flat distribution, which puts equal plausibility on each of the 4 outcomes. That's the binomial. That's what it would do in this case. B has the same expected value, right? One blue marble. It's the same expectation, but it has a different entropy because it reweights, but it has the same expected value. So again, read this section, you'll get an appreciation for it. If we oscillate it, flip it the other way, again, it's not binomial now, but it has the same expected value. Both of those distributions have less entropy than the binomial. And then something that's really uneven, but nevertheless still has the same expected value. How did I generate these? My computer, right? You can generate an infinite number of distributions that have the same expected value. The code's in the chapter. Has the same expected value, but it has way lower entropy. The binomial has the largest entropy of any distribution consistent with that constraint that the expected value be one blue marble. Yeah? Okay. So something a little bit more interesting. Maybe it's easy to see that when the expected value is, say, fair. We're going to draw two marbles, we expect one blue and one white. If that's the expectation, well, you have flat. That makes sense. What happens when the expected value is not fair? What about when the expected value is in excess of blue marbles? Same principles apply. Maximum entropy tells you what it should look like. It's a little bit less intuitive, but same thing. So what I'm showing you here is, this is a case where the expected value is 1.4 blue marbles over 2 trials. Yeah, you have to think about an aggregation of trials to get that. We expect there are 1.4 blue marbles in our big bag for every white marble. Yeah, so we're going to draw more. When we draw 2, we tend to get 1.4 blue marbles. So now what I do in the lower left of this slide, I've simulated a large number of arrangements of the possibilities, white, white, blue, white, white, blue, 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 that are consistent with that expected value. All of those distributions, I think I did 100,000 here, the code is in the chapter, have that expected value. And then what I'm plotting on the vertical axis is the density of them. How many of them have that entropy? For each of the distributions, I calculate their entropy, and then I plot out how many distributions have that entropy. And what the maximum entropy principle bets is that the distribution that occurs most often will have the highest entropy, because that's what it means. Right? That's all entropy means. It's the number of unique microarrangements of a system that will give you the same distribution, the same macro arrangement. And lo and behold, yes, on the far right margin, the distribution marked A, I highlighted here, is the binomial. It's the binomial distribution which the angels had previously descended to you and told you to use. It is exactly that distribution. It's the one that can arise the most ways. That's why we use it, because it's safe. It's the most neutral, like, I don't know, I'm only immortal, you're just telling me the expected value and I've got to like calculate predictions from that? Entropy. Use some entropy. Right? It's the opposite of arrogance. It's like saying, well, if I'm in this horrible state of mortality and all I know is that there's an expected value I'm calculating, lots of stuff could happen, but I don't have any information about that stuff. Let me choose a distribution that will minimize the information distance to what's really going on. Then you want the maximum entropy distribution, and then you want the binomial. Yeah? Does that make sense? It's a very modest information processing proposition, and this is why this maximum entropy principle ends up justifying good inferences in so many branches of statistics. It's this epistemological safeness position. Okay, with that, we're going to do next week is we're going to pick up here, and we're going to talk about generalized linear models. Believe it or not, from here, we end up deciding from what we know about outcome variables which likelihood function we can use. We will use the one that has maximum entropy for the constraints on that outcome variable. There aren't very many. Luckily, there are just a handful of distributions that will be relevant to us, so don't get terrified. When you return next week, I will give you a taxonomy, and we will do some actual statistics again, not just philosophy. Okay, with that, enjoy your weekends. I'll see you next week.